Insulated gate bipolar transistors, or IGBTs, can be implemented at various points within a 480-volt subpanel power distribution system to enhance protection, control, and efficiency. Understanding where to strategically place these components is crucial for optimizing system performance and safeguarding equipment. Let's examine the potential locations for IGBT implementation within the described setup, starting with the input to the 480-volt subpanel. IGBTs can serve as integral components within the main circuit protection scheme for the subpanel. Their primary advantage lies in their rapid switching capabilities, which enable them to effectively limit fault current. This is particularly important in preventing extensive damage to upstream equipment during electrical fault events. The fast response of IGBT allows them to quickly interrupt the current flow, minimizing the impact of the fault and protecting sensitive components. This capability is especially beneficial in industrial settings where electrical faults can lead to significant downtime and equipment damage. For instance, if a short circuit occurs downstream, the IGBTs can rapidly isolate the fault, preventing the fault current from propagating back to the main power source. This isolation minimizes the risk of cascading failures and ensures the continued operation of all the critical equipment connected to the same power system. Moving to the output of the 112 kV transformer and its connection to the disconnect switch, IGBTs can be employed within a soft starter circuit for the transformer. This application is particularly beneficial in mitigating inrush current, a phenomenon that occurs when a transformer is initially energized. Inrush current can be several times higher than the transformer's normal operating current, potentially causing stress on the transformer windings and other connected components. The soft starter, incorporating IGBTs, gradually increases the voltage applied to the transformer, thereby limiting the magnitude of the inrush current. This controlled voltage ramp-up prevents saturation of the transformer core, reducing the peak current drawn from the source. This is achieved by initially reducing the applied voltage to the transformer and gradually increasing it over a predetermined time. The IGBTs act as electronic switches, controlling the voltage applied to the transformer during the starting process. By limiting the inrush current, the soft starter minimizes the mechanical stress on the transformer windings, extending its lifespan and improving its reliability. Furthermore, it reduces the voltage dips that can occur on the power system during transformer energization, preventing disruptions to other sensitive equipment connected to the same grid. The section between the disconnect switch and the machine offers another strategic location for IGBT implementation. Specifically, IGBTs are commonly used in variable frequency drives, also known as VFD, to precisely control the speed and torque of the motor driving the machine. VFD offer numerous advantages, including improved energy efficiency, reduced mechanical wear, and enhanced process control. IGBTs within the VFD act as high-speed electronic switches, modulating the frequency and voltage supplied to the motor. This allows the VFD to adjust the motor's speed to match the specific demands of the application. For instance, if the machine requires a low speed for a particular task, the VFD can reduce the frequency of the applied voltage, thereby reducing the motor speed. Conversely, if a higher speed is required, the VFD can increase the frequency. This precise control over motor speed and torque translates into significant energy savings, as the motor only consumes the power required to perform the task at hand. Moreover, VFD can provide smooth acceleration and deceleration of the motor, reducing mechanical stress on the machine and extending its lifespan. The use of IGBTs and VFD also enables advanced motor control algorithms such as closed-loop feedback control, which further improves the accuracy and responsiveness of the motor control system. This is particularly important in applications requiring precise positioning or speed regulation. Several additional factors warrant consideration when implementing IGBTs in this power distribution system. Firstly, the specific locations and applications of IGBTs can vary depending on the specific equipment being used and the overall system design. A thorough assessment of the system requirements is essential to determine the optimal placement and configuration of IGBTs. Secondly, the size and ratings of the IGBTs must be carefully selected to match the load requirements and intended protective functions. The IGBTs must be capable of handling the maximum current and voltage levels expected in the system, as well as withstanding any transient surges or fault currents. Selecting IGBTs with adequate ratings ensures reliable operation and prevents premature failure. Thirdly, proper installation and maintenance of the IGBTs are crucial for ensuring optimal performance and safety. IGBTs are sensitive electronic components that require careful handling and installation. Proper heat sinking is essential to dissipate the heat generated during operation, preventing overheating and damage. Regular maintenance, including inspection and testing, is necessary to identify any potential issues and ensure the continued reliable operation of the IGBTs. In summary, IGBTs can be strategically implemented in a 480-volt subpanel power distribution system at several key locations, including the subpanel input for circuit protection, the transformer output for inrush current mitigation, and the machine connection for motor control via VFD. Careful consideration of system requirements, proper component selection, and adherence to sound installation and maintenance practices are essential for realizing the full benefits of IGBT technology. IGBTs can provide fast switching capabilities, which can limit fault currents and protect upstream equipment at the input to the 480-volt subpanel. At the output from the 112 kV ampere transformer to the disconnect switch, IGBTs can be used in a soft starter circuit for the transformer. This can reduce the inrush current and prevent damage to the transformer and other components downstream. From the disconnect switch to the machine, IGBTs can be used in a variable frequency drive to control the motor speed and torque. This can improve efficiency and reduce wear on the machine. Remember, the specific locations and application of IGBTs may vary depending on the equipment and system design. The size and ratings of the IGBTs used should be carefully selected to match the load requirements and protective functions. And proper installation and maintenance of the IGBTs are crucial for optimal performance and safety. The goal of input protection for the 480-volt subpanel is to protect the subpanel and the equipment connected to it from overcurrents and short circuits. IGBTs are fast-switching devices that can be used to quickly interrupt the flow of current in the event of a fault. This helps to prevent damage to equipment and personnel. IGBTs can be used to reduce the inrush current when the transformer is first energized. Inrush current can be several times the normal operating current of the transformer and can cause damage to the transformer windings and other equipment. IGBTs can be used to gradually increase the voltage to the transformer, which reduces the inrush current. VFD are used to control the speed and torque of motors. IGBTs are used in VFD to switch the voltage to the motor on and off rapidly. This allows the VFD to control the frequency of the voltage applied to the motor, which in turn controls the speed of the motor. The location for the IGBTs can vary depending on the specific application. However, some common locations include the input to the 480-volt subpanel, the output from the 112 kV ampere transformer to the disconnect switch, and the disconnect switch to the machine. The size of the IGBTs will depend on the amount of current that they need to carry. The ratings of the IGBTs will depend on the voltage and current that they need to withstand. IGBTs should be installed according to the manufacturer's instructions. They should be properly heat-sinked to prevent them from overheating. IGBTs should be inspected regularly for signs of damage. If any damage is found, the IGBTs should be replaced. The purpose of IGBTs within the main circuit protection for the subpanel is to provide a fast and reliable means of interrupting fault currents, thereby protecting the subpanel and upstream equipment from damage. IGBTs achieve this by acting as high-speed electronic switches that can quickly disconnect the circuit in the event of an overcurrent or short circuit. IGBTs can respond much faster than traditional circuit breakers, limiting the magnitude and duration of fault currents. This is particularly important in modern electrical systems where sensitive electronic equipment is susceptible to damage from even brief overcurrent events. The location of IGBTs within the subpanel circuit protection scheme is typically in series with the main incoming power conductors. This allows them to interrupt the current flow to the entire subpanel in the event of a fault. The IGBTs are controlled by a protection relay that monitors the current flowing through the subpanel. If the relay detects an overcurrent or short circuit, it sends a signal to the IGBTs to open the circuit. The size of the IGBTs used for circuit protection must be carefully selected to handle the maximum fault current that the subpanel is likely to experience. The ratings of the IGBTs must also be sufficient to withstand the voltage and current stresses imposed during a fault event. The purpose of using IGBTs in the soft starter circuit for the transformer is to reduce the inrush current that occurs when the transformer is initially energized. Inrush current can be several times higher than the transformer's normal operating current, potentially causing stress in the transformer windings, voltage dips in the power system, and nuisance tripping of circuit breakers. IGBTs in the soft starter gradually increase the voltage applied to the transformer, limiting the magnitude of the inrush current. This is achieved by controlling the firing angle of the IGBTs, which determines the portion of the voltage waveform that is applied to the transformer. By gradually increasing the voltage, the soft starter prevents saturation of the transformer core, which is the primary cause of inrush current. The location of IGBTs in the soft starter circuit is typically in series with the primary winding of the transformer. The IGBTs are controlled by a soft starter controller that monitors the voltage and current applied to the transformer. The soft starter controller gradually increases the firing angle of the IGBTs until the transformer reaches its full operating voltage. The size and ratings of the IGBT used in the soft starter must be carefully selected to handle the transformer's inrush current and operating voltage. The soft starter controller must also be properly configured to provide the appropriate voltage ramp-out profile for the transformer. The use of IGBT in a variable frequency drive to control the motor speed and torque offers several advantages over traditional motor control methods. Firstly, VFD provide precise and efficient control over motor speed, allowing the motor to be operated at its optimal efficiency point for a given load. This can result in significant energy savings compared to operating the motor at a fixed speed and using mechanical methods to adjust the output. Secondly, VFD can provide smooth acceleration and deceleration of the motor, reducing mechanical stress on the driven equipment. This can extend the lifespan of the motor and the connected machinery. Thirdly, VFD can provide overload protection for the motor, preventing damage from excessive torque or current. The location of IGBTs within the VFD is in the inverter section, which converts direct current voltage to alternating current voltage with variable frequency and amplitude. The IGBTs act as high-speed electronic switches, rapidly turning on and off to create the desired alternating current waveform. The VFD controller modulates the switching frequency and pulse width of the IGBTs to control the voltage and frequency applied to the motor. The size and ratings of the IGBTs used in a VFD must be carefully selected to handle the motor's current and voltage requirements. The VFD controller must also be properly programmed to provide the appropriate voltage and frequency control for the motor. Firstly, consider the specific requirements of the load. This includes the voltage, current, and power requirements of the equipment being powered by the subpanel. The IGBTs must be sized appropriately to handle these requirements without overheating or failing. Secondly, consider the protective functions that are required. This may include overcurrent protection, overvoltage protection, and undervoltage protection. The IGBTs can be used in conjunction with other protective devices, such as fuses and circuit breakers, to provide comprehensive protection for the equipment. Thirdly, consider the environmental conditions in which the IGBTs will be operating. This includes the temperature, humidity, and vibration levels. The IGBTs must be rated to operate reliably under these conditions. Proper installation and maintenance are essential for ensuring the long-term reliability of the IGBTs. This includes proper heat sinking, wiring, and grounding. The IGBT should also be inspected regularly for signs of damage or wear. IGBTs have many other uses too. Firstly, IGBTs are used in induction heating applications for precise power control. Secondly, they provide efficient switching in uninterruptible power supplies for reliable backup power. Thirdly, they are used in electric vehicles for traction motor control, improving energy efficiency. Fourthly, they are used in solar inverters for converting DC power to AC power. Fifthly, they are used in wind turbines for grid connection and power management. Sixthly, they are used in medical equipment such as MRI machines and X-ray machines. Seventhly, they are used in welding machines for precise current control. Eighthly, they are used in high-frequency power supplies for various applications. Ninthly, they are used in active power factor correction circuits to improve power quality. Tenthly, they are used in railway traction systems for efficient power conversion and control. Proper installation and maintenance of IGBT modules are essential for ensuring their reliable operation and long lifespan. Firstly, select appropriate heat sinks to dissipate heat effectively, preventing overheating. Secondly, apply thermal grease or pads between the IGBT module and the heat sink to improve thermal conductivity. Thirdly, ensure proper mounting torque to maintain good contact between the module and the heatsink. Fourthly, use appropriate wiring techniques to minimize inductance and voltage overshoot. Fifthly, protect the IGBT module from overvoltage and overcurrent conditions using appropriate protection devices. Sixthly, regularly inspect the IGBT module and heatsink for signs of damage or contamination. Seventhly, keep the IGBT module and heatsink clean to maintain good thermal performance. Eighthly, follow the manufacturer's recommendations for storage and handling. Ninthly, use appropriate test equipment to verify the performance of the IGBT module. Tenthly, train personnel on the proper installation and maintenance procedures for IGBT modules. When selecting IGBT for a specific application, several key parameters must be considered to ensure optimal performance and reliability. Firstly, voltage rating is the maximum voltage the IGBT can withstand without breakdown. Select a rating significantly higher than the application's maximum voltage. Secondly, current rating is the maximum continuous current the IGBT can handle. Choose a rating that exceeds the application's peak current requirement. Thirdly, switching frequency is the rate at which the IGBT can switch on and off. Higher frequencies allow for smaller and more efficient designs. Fourthly, on-state resistance, often designated RD-SUN. This is the resistance when the IGBT is fully on. Low values minimize power dissipation and improve efficiency. Fifthly, gate charge is the amount of charge required to switch the IGBT on and off. Lower gate charge results in faster switching and reduced power consumption. Sixthly, thermal resistance is the resistance to heat flow from the IGBT junction to the ambient environment. Lower thermal resistance allows for better heat dissipation. Seventhly, package type is the physical housing of the IGBT. Select a package that provides adequate thermal performance and mechanical protection. Eighthly, operating temperature range is the range of temperatures within which the IGBT can operate reliably. Ensure the application's temperature range falls within the IGBT specifications. Ninthly, short circuit withstand time is the duration the IGBT can withstand a short circuit condition. Select a value that meets the application's protection requirements. Tenthly, gate threshold voltage is the voltage at which the IGBT starts to turn on. Choose a value that is compatible with the gate drive circuitry. Always consult the manufacturer's datasheet for detailed specifications and application guidelines. When troubleshooting issues with IGBTs, consider a systematic approach to identify the root cause of the problem. Firstly, check the gate drive signal to ensure it is within the specified voltage and current levels. Secondly, inspect the IGBT for signs of physical damage, such as cracks or burns. Thirdly, measure the voltage and current across the IGBT to verify they are within acceptable limits. Fourthly, use a multimeter to check for shorts or opens in the IGBT terminals. Fifthly, use an oscilloscope to examine the switching waveforms and identify any anomalies. Sixthly, verify the thermal management system is functioning correctly, ensuring adequate heat dissipation. Seventhly, check the surrounding components for any signs of failure, such as capacitors or resistors. Eighthly, review the application's operating conditions to identify any potential causes of stress on the IGBT. Ninthly, consult the manufacturer's datasheet for troubleshooting tips and application notes. Tenthly, replace the IGBT with a known good unit to rule out a defective component. Remember to always follow proper safety precautions when working with electrical equipment. When working with power distribution systems involving IGBTs, it's crucial to understand relevant safety standards and regulations to ensure a safe working environment and prevent accidents. Firstly, adhere to the National Electrical Code, or NEC, which provides comprehensive guidelines for electrical installations in the United States. Secondly, comply with Occupational Safety and Health Administration, or OSHA, regulations for workplace safety, including lockout-tagout procedures and personal protective equipment requirements. Thirdly, follow the guidelines of the Institute of Electrical and Electronics Engineers, or IEE, for electrical safety in industrial and commercial power systems. Fourthly, consult the standards of the International Electrotechnical Commission, or IC, for international electrical safety requirements. Fifthly, ensure that all electrical equipment is properly grounded to prevent electrical shock hazards. Sixthly, use appropriate personal protective equipment, such as insulated gloves, safety glasses, and arc flash suits, when working on electrical equipment. Seventhly, implement lockout-tagout procedures to de-energize equipment before performing maintenance or repairs. Eighthly, provide regular safety training to employees on electrical hazards and safe work practices. Ninthly, conduct regular inspections of electrical equipment to identify and correct any potential safety hazard. Tenthly, maintain accurate records of electrical system maintenance and repairs. Always prioritize safety when working with power distribution systems. IGBT modules are commonly used in various applications due to their efficient switching characteristics and ability to handle high power levels. Here are some specific examples. Firstly, in variable frequency drives, or VFDs, IGBT modules are used to control the speed of electric motors in industrial applications such as pumps, fans, and compressors. Secondly, in uninterruptible power supplies, or UPSs, IGBT modules provide a reliable source of backup power during power outages, ensuring continuous operation of critical equipment. Thirdly, in solar inverters, IGBT modules convert the direct current, or DC, power generated by solar panels into alternating current, or AC, power for use in homes and businesses. Fourthly, in welding machines, IGBT modules control the current and voltage used to create a weld, providing precise and efficient welding performance. Fifthly, in electric vehicles, IGBT modules are used in the traction inverter to control the speed and torque of the electric motor, enabling efficient and responsive acceleration. Sixthly, in induction heating systems, IGBT modules generate the high-frequency current used to heat metal parts for various industrial processes. Seventhly, in medical imaging equipment, such as MRI machines, IGBT modules provide the high power and precise control required for generating magnetic fields. Eighthly, in railway traction systems, IGBT modules are used in the traction inverter to control the speed and torque of the electric motors that power the train. Ninthly, in power factor correction circuits, IGBT modules are used to improve the power factor of electrical systems, reducing energy waste and improving efficiency. Tenthly, in active filters, IGBT modules are used to mitigate harmonic distortion in electrical systems, improving power quality and preventing equipment damage. IGBTs contribute to energy efficiency and sustainability in various applications. Firstly, they enhance the efficiency of variable frequency drives, reducing energy consumption in motor-driven systems. Secondly, they enable efficient conversion of solar energy in solar inverters, promoting renewable energy use. Thirdly, they improve the efficiency of electric vehicles, reducing greenhouse gas emissions and dependence on fossil fuels. Fourthly, they contribute to the efficiency of uninterruptible power supplies, minimizing energy waste during backup power operation. Fifthly, they enable efficient power factor correction, reducing energy losses in electrical systems. Sixthly, they enhance the efficiency of induction heating systems, minimizing energy consumption in industrial heating processes. Seventhly, they contribute to the efficiency of welding machines, reducing energy waste during welding operations. Eighthly, they enable efficient power conversion in railway traction systems, reducing energy consumption in train operation. Ninthly, they improve the efficiency of lighting systems, reducing energy waste in residential, commercial, and industrial settings. Tenthly, they enable the development of more efficient and sustainable power grids, facilitating the integration of renewable energy sources and reducing overall energy consumption.